So hi everyone, I actually started recording this video yesterday, and after recording a few of them I just found out that there's still a problem in my microphone, and thus I had to re-record everything because otherwise it was just the irritating sound all over again. So in this videos we are going to actually cover up a few of the things that you have asked about in yesterday's lecture regarding the processes and regarding the Linux way of doing multi-threading, and also partially how Windows does it. But as I told some of you after the lecture, I have never done concurrent programming on Windows, although I totally know that it's possible because most of the games just run on Windows, and games are among the most multi-threaded programs probably written on Earth, or at least some of them, of course. So let's start by basically taking a look at the Linux process abstraction. And as I repetitively said, Linux basically has a unique implementation of processes. It does not differentiate between threads and processes. All of them are called tasks, and the way that the only difference to Linux between a thread and a process is conceptually that threads in Linux can share memory versus processes which cannot share memory, basically. So the way that Linux implements threads and processes, both of them, is that they are called tasks. They are stored in special structures, special operating systems structure that we are going to take a look at today. And I'm basically using some flags, some configurations. You can basically change if this task can shares other memory, for example, with other tasks or not, and then that would be your thread. But if it doesn't, then this will be your process. Okay, and there are two abstractions that we need to understand here. The first one is the concept of a virtual processor, and the second is the concept of a virtual memory. We have actually touched upon both of them a little bit in the normal lectures. So threads share the virtual memory abstraction, and that is basically that all threads, well, they share them in two ways, basically. The first way is that if the threads are actually running such that they are supposed to share memory together, then they basically share the actual virtual memory together. But also, I mean, we have also talked a bit about how virtual memory is mapped into real memory using hardware in the second lecture, I believe. And that's basically also another shared abstraction. So all threads basically see the memory almost equally. You do not really have to point to memory address number 1 million, but rather to go in sequence as if you own the whole memory, basically. But each one of them receives its own virtual processor, and what we mean by virtual processor here is that the amount of time allocated to each thread to run to do whatever it is supposed to do. And when we talk about a program, we are not talking about the process that is running, but rather about the process and but rather about the process and all related resources. So a process is both the program and the related resources, so open files, address space, memory access, and so on. And everything, as I said, is called tasks, basically. So where do we find the task structures? We find them in /include/linux /sched.h, and this is where the task structure is. And all task structures form together a linked list, a doubly circular linked list that is called the task list. And you might want to remember what a circular doubly linked list is, but just basically either going back to your previous courses or going to your Wikipedia page. But anyway, so you have a circular doubly linked list that's called the task list or a task array. And it basically stores this structure: struct, task, struct. for each basically element in the linked list. And the task struct is basically what describes what a thread is. So each thread owns a task struct, and that task struct has, for example, the state of the thread. Is it runnable? Is it unrunnable? Is it stopped? Where is the stack of the thread? And things such as per process flags. So you might have some flags that we're going to talk about in a bit more details, but also some things that are related to scheduling. So for example, the priority of this thread when it comes to scheduling. Is it static priority, normal priority, and also what scheduling clause will it use. And this is actually, I mean, we cannot basically cover everything in this structure because, well, it's kind of long. It has 500 lines. You might want to go through them on your own. Some of them are very well described. Some of them are just like, well, you need to find out what they do. And you're not going to really, in real life, be changing a lot in the task struct, okay? And it is actually as a side effect of having 500 lines. I mean, that's the struct size. That's the amount of information that the struct stores, basically. You basically have 1.7 kilobytes for each task, or for each thread, or for each process running on Linux to just describe that task or that process or that thread. And that's on a 32-bit machine. So you can actually pretty easily calculate if you have an 8 gigabytes machine, for example, memory, in memory, basically, if you have 8 gigabytes of memory on your machine, by dividing the 8 gigabytes by 1.7 by the 1.7 kilobytes, that's the absolute maximum number of threads that you can store in your memory, right? But that's a completely theoretical number. It doesn't mean anything because you will break much faster than this, because your memory stores other things besides just the task struct of the threads. It stores the stack, the heap, and so on and so forth. But I mean, just if you have just empty threads, you can basically calculate the theoretical maximum number using that. And well, depending on your machine, you might even get blocked by the number of bits that you have in your registers, and we are going to talk about this in a bit more detail later in the course. Now that we have actually seen how the struct looks like, I mean, let's just look at a graphical figure of how the task list looks like. You basically have the struct task struct, which is basically described each thread, and you have a doubly linked list, so you have it linked to the one that follows and the one that is before it, and this is basically your task list. So it's a circularly doubly linked list, and this is it has some few details that might be a bit different from what you have studied in your algorithms, but the concept itself is exactly the same. I mean, the implementation might be different, but the concept itself is exactly the same. And as we have spoken about that there are different process states, so if each one of these processes / tasks / threads can be in one of many states, basically. And basically, the way that a thread starts is that some existing task calls fork and creates the new process / the new thread / the new task. I mean, they are all equivalent in Linux. I cannot emphasize that more. And then you basically go into a queue of tasks that are ready to run but not running yet. Okay, and everything here in capital is basically a flag that stores the state of your task. So by setting the task running state to something, like for example, if you remember here, we had the state as unrunnable, runnable, or stopped, for example. So this basically says that, okay, this is runnable, unrunnable, or stopped. And it will lie based on what you set to some of these states, basically. So you have some task list, well, some number of tasks that are waiting to be scheduled on the processor. Once the scheduler dispatches one of the tasks to run, and that's basically by calling context switch, a function that you can actually search for in your code, in your Linux kernel code, you basically move to a running state. And in your running state, you have one of a few options. You can be preempted and go back to ready to run, but not running. And that's basically if you get something like timer interrupt. And we have talked about the timer interrupts as basically you allocate some time for the process to run on the processor, and after that time you evict that task so that other processes get also some share of the processor. And that's your virtual processor abstraction. Okay, but it can be also that you got some higher priority task interrupting your work, so you move that task there and you move the higher priority task here. Okay, the task can finish also, so task gets terminated, and that thus it calls a do exit. We're going to discuss this in a bit more details. And the task can also be blocked on some data, for example, fetching data from memory or fetching or opening some file from hard disk. And I mean, from the hard disk, you typically read into the memory because that's the only path you have. So I mean, you might get blocked for a few milliseconds or even seconds waiting for something to happen, waiting for a network packet or something. And then the task sleeps on some wait queue for a specific event. And you wait here in the wait queue. And there you have basically two flags that you might want, that basically control what triggers you to go out of your waiting. And one of them is task interruptible and the other is task uninterruptible, and we are going to discuss them in the next two slides. But anyway, so moving from task interruptible or task uninterruptible, which are basically both meaning waiting, some event happens and you basically go back to the task running state and then wait for your time to get scheduled on the processor. So what is task interruptible and what is task uninterruptible? An interruptible task is basically a task that is sleeping and that can get that can move from the sleeping state, from the waiting state to the runnable state, either when some condition exists, so you're waiting for a network read, for example, or for a file to open, but also the process can wake prematurely and become runnable if it receives a signal. And that signal basically can be, for example, I mean, you might be waiting for some event to happen, but you can also wait for a signal that comes from the actual kernel. And that signal can be something different, okay, than just waiting for the event to happen. So you can move to the task running state by either of these two conditions. One of them is that you're waiting for some condition to exist, some event, and waiting for a network packet to arrive. Okay, that's one way. But the other way is that the kernel wakes you up for some reason. Okay, and that reason is of course very, very dependent on your thread. Okay, and a task uninterruptible is exactly like a task interruptible, except that it only wakes up when the condition happens. Okay, and it cannot wake up if it receives a signal from the kernel. So the only way for this thread to rerun is to basically, or to go from the waiting state to the runnable state. The only way is for that event to happen. Otherwise, it will stay in the waiting state. And this is used in situations where the process must wait without interruption. I mean, again, it's very program specific, and or when the event is expected to occur quite quickly. So you expect that, well, this event is going to happen in a blast. So you then put it as task uninterruptible. But in general, you use this flag much less often when you basically are doing threading inside the kernel. Okay, when you're playing with the actual kernel, you use that flag much less often because it basically reduces your chances as a thread to move from a waiting state to a runnable state. So let us look at the code that actually changes the state of the process or of the task. And you can see here that there is set current state that basically changes the state of the current running process using the different the different flags that we have mentioned, and one of them is, for example, task uninterruptible, and it basically goes to the current state, the current task state. So it basically puts in the current task, change the state of the current task to the state that it actually thinks it was called to change it with. And these flags are actually also defined. If you just go on the code and just press F3 on, for example, task uninterruptible, or do a search on these flags, you'll find them defined in sequence. So there are multiple of these flags that are defined. And there is also a set task state. So this was set current state, and that's basically for the current task. But there is also a set task state, which is for another task, which takes task the task that you are trying to change the value for or the state for that task as input, and the state value. Okay, so these are basically the ways that the states are changed in the kernel. So the process tree is a concept in Linux where you basically have all the processes as descendant from the init process. We have actually mentioned that in the class, that we have the init process, the father/mother of all processes that runs on Linux, and init always has a PID of 1. Okay, and this is basically the process that the kernel, when the kernel loads and starts, this is the very first process that starts. And the relationship between the processes is stored in the process descriptor, which is in the task struct. And each task struct has some fields to basically say what is the parent of this task, but also what are the children of this task. So this is actually the code from the task struct that basically shows you where's the parent and where are the children and siblings, which are basically the siblings that they are on the same process. They're on the same level when it comes to when they were forked, basically. And also some other things that you might need, such as who's the group leader of these tasks. But in general, you can actually go through the whole process tree by just looking at your own process, right? Because basically, if you iterate until you reach the topmost process, then you can actually reach init. And from init, if you look at all the descendants of that process, then you can see all the descendants in the Linux system, because init will have all the other tasks that got spawned afterwards as descendants of init, and basically in tree. And you can basically use this call to get the parent of your current process, of your current thread, and you can use basically also this to go through the children of your process. Yep. So this is basically the code you would need to basically go through the children of the current process that is running. So that means you can iterate from the top to the bottom. And to get to init, it's actually quite simple. You basically have the task struct that you're looking at, and the task, and you pick the current task, and as long as the task is not equal to init task, it's not equal to 1 basically, go to the parent, sorry. And then in the for loop you don't really need to do anything, because the for loop will just go all over until it basically reaches the parent. Of course you can print, or you can use print key to print whatever task you're on. You can do stuff inside, but to get to the init process, this is all you need basically. So a question arises. It's actually very simple code to implement, and I advise you to try it. And that's how do you print all PIDs using just the task struct of your process. That's not something that I want you to do for an assignment or anything, but it's actually fun to take a look at things in that way, and basically do things with your own hand. And there are even macros that have been added to the Linux kernel to make our lives easier to basically navigate through the tasks. As we said, you have basically a doubly linked list, circular linked list. So it's actually very easy to jump from each task to the next one. And there's a macro that basically defines next task, and from which you can basically get the next task to the task you're in right now. Okay. And there is also another macro which is for each process, and you start from a task, iterate over all the it iterates over all the tasks basically, and that basically means that you start from your current task but go through the whole task tree. And here's a question: should we use for each process task a lot? What do you think? Do you think it's a good idea to basically have it all over the Linux kernel to do this sorts of things, or is it something that you use with care, and why? So now that we have looked at how tasks are actually implemented in Linux, let us look a bit more into how the stuff we have talked about for the past few lectures actually work. And these are basically fork and exec. And we have talked about the Linux philosophy of having fork and exec, and that fork basically copies the parent and creates the new child as a copy. And the way that fork is actually done, it would be completely stupid and completely redundant if you basically take the parent, copy everything that is related to the parent, as in basically copy the data that the parent owns, and then after 1 millisecond, after you have done that process, which is kind of expensive because it's 1.7 kilobytes of data that you're copying, and as we said that the kernel should be very efficient. So now that you have copied that amount of data, then the next millisecond or microsecond, you just remove them, delete them, and just load the new program. That's pretty stupid, right? Because you're basically wasting 1.7 kilobytes of data that you copied while they are completely useless. So the way that fork is implemented is that it uses a technique that is called copy on write pages. What happens when you call fork is that you start a process or a new task that actually points to the same data that the parent owns. So it doesn't copy the parent's data. It points to the same stack, to the same heap, points to everything that the parent owns. And you mark it such that if any writing is being done in the child, if the child is supposed to basically use the exact same data and it's just a replica of the parent, then you basically start the copying process. Okay? Then you start making the duplication. But if not, if the child basically calls exec right after it starts, after the fork basically, then the data, the exec call will basically replace or will start a new clean structure for the child, and copy the new program right away to the child, instead of basically copying parent's program, removing parent's program, and copying child's program. So instead you just copy the child's program. And in this way, you save quite a bit of both memory bandwidth, or basically operations. I mean, it's not really memory bandwidth, but it's more operations that you're saving, and makes the whole process faster. Okay, so the fork is basically implemented in kernel/fork.c, and it is mostly memory stuff. It is mostly memory related work. And you find this very interesting note in the beginning of the fork.c class that basically says that fork.c contains the help routines for the fork system call. See also entry.s and others. Okay, because these are the different system, the different things that would help you to understand the system calls. Fork is rather simple, which it is, right? It's just, it has a few tweaks, but once you get it, it's right. Once you get the hang of it. But the memory management can be a c memory.c copy page range. So the hard part here is actually in the memory management. It's not the actual forking. Okay, and this is the fork.c program. It basically the stuff is actually done in, I mean, in this is the real stuff. This is what actually does the stuff. It's underscore do fork. There's another call that is called do fork, which is the real thing that you call. But this is where the do fork basically calls this function to do the real stuff. And basically it copies the process, and if successful, kickstarts it and waits for it to finish using the virtual memory if required. Okay, and you find that, I mean, it's not an entirely easy read, but you can get the hang of it if you try to. I mean, it's not the worst part of the Linux kernel that is written, and it is actually a bit documented also. But actually, do fork is not even the place. I mean, do fork does a lot of checks on the flags and on the states of the machine and on the errors, but the actual sweet stuff is even done in copy process. So you have a do fork that calls underscore do fork that calls copy process, and copy process is, this is where the real meat is actually in the forking process. It basically creates the new process and a copy of the old one, but does not actually start it yet, because as we said, you don't start until you're scheduled basically. It copies the registers and all the appropriate parts of the process environment as per the clone flags. I mean, you have basically in Linux something that is called the clone flags, and these are the flags that control what is shared between the parent and the child process that is being forked. And the actual kickoff is left to the caller. So, and this is the caller basically. And then you have basically a long process that does everything that is related to actually copying the process, or making the replica of the process, managing that, doing the copy on write protocol, and so on. Okay. So the interesting work, as we said, is done in copy process, and this is basically a list of the things that copy process does. It basically creates a new kernel stack, thread infrastructure, and task structure for the new process. Right now, both the child and parent process are identical, because I mean, it's just replicating it. And then it checks that the child is actually allowed to be spawned, because the child might be, as we said that during the class, you might have a limit on the number of children that this process can start, and you check that you're not exceeding the resource limits on the number of the processes. You set some initial values in the process descriptor in basically the task struct that you just created, and you set the child states to task uninterruptible to ensure that it does not yet run, because, well, task uninterruptible, as we said, will not run on a signal, for example. So it will just run when the event that it is waiting for happens, and that event is basically the actual creation of the child process. or of the child thread or of the child task. Okay. You update the flags of the task structure, including, for example, things such as the if the process has not called exec yet. So this is again another flag that basically says that this process has not called exec, and that basically tells the operating system, the kernel, that okay, this process has not yet copied the data from the other program that it is supposed to run. And now if this process starts writing or reading, then I need to copy the data of the parent again. Then allocates a new PID to assign that new PID to the new task, now that the task is in a much better state. So I mean, there is a replica, but then now you have a complete structure almost for the task. You start giving the task an ID, a PID, and then you basically, as the scheduler tries to schedule things, I mean, there is a PID now for this, but it will not be scheduled yet because you have the task uninterruptible up. And then you basically, depending on the flags passed, you basically set up the sharing settings between the parent and the other and the children, or that child and other children of that parent, for example, siblings basically, and clean up and return the caller to the caller pointer to the new child. Now that the copy process is done, the do fork can actually do what it is supposed to do. And what the do fork tries to do is that it tries to run the child first. And the reason that do copy tries to run the child first, so I mean, once this returns, as we said that, well, you have do fork that calls this, and once that calls basically this here, okay, once you get P, you try basically to make P run before the parent. And the reason you do that is that you want to make sure that if P is going to call exec, then there is no need to copy to the data of the parent, because it might be actually problematic if the parent starts running before the child, and then the parent starts changing things in its own stack, or in its own basically data or flags, because that would basically mean that you also need to do the copy for the child, because otherwise the state of the data now is changed. So you need to make a replica at least of the things that are not going to be shared between the child and the parent. Okay, so then do copy basically runs the child first. There was there is a call that is called vfork, which is basically done also in do fork. I mean, it's again a system call that you can call, and vfork is much less used than forking now, than normal fork, because the child executes basically, I mean, when you call vfork, you basically again use the same forking mechanism that we talked about, but using the flags. Vfork just raises another flag that basically says that this is not a normal fork, this is a vfork. And a vfork is a bit dangerous. Its semantics are not very safe. So you basically it basically starts by the child executing as the sole thread in the parent's address space, and the parent is completely blocked until the child either calls exec or exits. So using vfork, you start the child and the parent gets blocked, absolutely, cannot run, until the child calls exec, and then the child basically will spawn the new program, or the child exits, and then the child has gotten sole control over the parent's address space and the parent's basically task struct. Okay, and this should be used seldom. It shouldn't really be used, because there is usually a problem if exec if the child is supposed to call exec, but the child fails before it actually calls exec. And that basically means that the parent is blocked, and you have some uncertainty in your kernel that would be, I mean, that you can of course handle with basically some extra calls and stuff, but it's still, I mean, the amount of uncertainty and the amount of work that you would need to do to basically make sure that things are not broken is more than you would hope it would be. So now that we have actually talked about how forking is done in Linux, let us go to the sweet parts where you had some trouble during the lecture. So I said repeatedly that there is no concept of threads in Linux. It is just a task, and that means that there are no special scheduling semantics or data structures to represent threads basically in Linux. So they are just like any normal process, and that each thread has a unique task struct and appears to the kernel as a normal process. And they just look like basically processes that share some resources such as address space or with other processes. Okay. In Windows and Solaris, threads are actually called lightweight processes, and they are basically different. I mean, it's a very different mindset. You have a process, and you have a thread or a lightweight process, and a thread is much lighter as an abstraction compared to a process. This is actually some benchmarking of spawning threads, creating processes versus creating threads in Windows 7 on a pretty good machine. I mean, an i5 3.2 gigahertz machine, so it's not that ancient. And you can see that creating a process on average takes around 13 milliseconds, while creating a thread takes on average 0.03 milliseconds. So the time required to create a process is 340 times on average the times required to actually create a thread. And that is a completely different mindset compared to Linux, because in Linux both threads and processes are just the same, while in Windows you really on Solaris, which is kind of dying, in Windows and Solaris you really have to think, when do you want to thread and when do you want to spawn a new process, because the cost and the as in time required to start such a thread or a process is very significantly different. And basically this is a huge difference. And here comes the Windows versus Linux. What is the difference between the implementation of these two? But let us first ask a question, which is basically compare the implementation between Linux and Windows if you're writing a multi-threaded program, assuming that you have a process that consists of 4 threads. So if you have a process that runs basically 4 threads, in Linux it will be implemented differently compared to Windows. Can you think of how they are different? So let's go back to how threads are created in Linux, just to basically finalize this. And these are basically the flags that the clone flags that are used to basically set up the way that the threads are created in Linux versus, so using these using these flags, you control how a thread is actually created and what is shared between the different threads, what is shared between the thread and the parent. And if you're going, for example, for a vfork, so this is a clone vfork flag that basically tells the do copy call to basically start vfork instead of a normal fork, and so on. So these are basically all the flags that you need to parameterize how your thread creation works in Linux. Okay. Now this is where people had troubles. Kernel threads. Let's talk about kernel threads in Linux, because they are just quite simple. I mean, all threads are equal in Linux, and that basically means that kernel threads are not really that different in how they are created and how they are managed in Linux. I cannot emphasize that more. And the kernel thread is basically a standard process that exists solely in the kernel space. And it is basically something that is used by the actual kernel to do things, to run actually kernel specific tasks. So it is in the context of Linux, when we talk about kernel threads, then we are actually talking about threads that do stuff for the kernel and has nothing to do with user space threads. And this is again where kernel threads are actually implemented. It's in kthreads.c, and there you basically have quite a good description of what this does and how does this differ from normal threads. And you have basically kthread create on node for that. Okay, so what is the difference between kernel threads, user level threads, and kernel supported threads? And I never talked about kernel supported threads before, but let's just say that it is a complete mess. Let us start by the very easy ones. There is the concept of user level threads, which are also called in some textbooks green threads. And these are basically threads that are completely unknown to the operating system. These are the threads that we talked about in the lecture that basically do not appear to the operating system in any way and do not affect, the operating system is completely unaware that these threads exist. And you can make a hack using upcalls that to basically make the kernel schedule threads. And this is what I talked about in the lecture, that you might want the actual thread scheduling as an application for yourself. And this is in the book in section 4.8.2. There is a description of that. And this was the main way to do threading before. There was nothing else compared to this. And it sucked. It really sucked because it required a lot from the programmer to actually get the thread scheduling to be correct. Okay, now that we are done with these, and let's talk about kernel threads. And well, let's say that they are, in the context of Linux, they are mostly operating system related threads, and they just do operating system related stuff. Remember, for example, when we talked about when a thread dies or when a thread goes into finished state, you need a kernel level thread to basically handle the actual cleaning up of everything. But, and this is, as I said, it's a mess. This is also used in many systems to actually have kernel supported threads. And in many systems, you basically do not differentiate between the kernel supported threads and kernel threads, as in terminology wise. So what are kernel supported threads? Again, this is a mess more than the previous mess. What the kernel supported thread doesn't not just depend on the operating system, but also on the threading library and on the programming language. So it's something that basically tells you that these threads the kernel can schedule. Basically, they are user level threads that the kernel can schedule. Okay, so let us dive a bit even deeper on what kernel supported threads are. And this is when threading models comes to play. There is the many-to-one model, where many user level threads are basically mapped to a single kernel thread, and this is usually done on a single processor. This model is obsolete and nobody actually uses it because it actually defeats the purpose of having threading anyway, because there are user level threads and that you need to manage basically by doing scheduling on your own. There's the one-to-one model, which is the model that we use in most operating systems actually. Until recently Windows was not like that, but now it's like that also. And Linux has always been like that, and that each user level thread is mapped directly to one kernel thread, and that's it. So, then the operating system basically does not have to differentiate between what the user level thread is and what the kernel level thread is. And one thing to note about the one-to-one model is that this doesn't really change with the number of processors you have, because at the end of the day, if you have a single processor, if you have multiple processors, it doesn't matter, right? It's a one-to-one. And this is why I have always been talking about kernel threads as, I mean, there isn't really a difference between user threading and kernel threading, okay? And that is the Linux model, and this is how most Windows operating systems work right now. Now there's the many-to-many threading model, where you have basically, where you have many user threads mapped to many kernel threads. And it can be basically, the number of kernel threads can be smaller or equal, which just makes it more fun, the number of kernel threads. So you have 50 user level threads that gets mapped to 5 kernel level threads, for example. And then there are 10 user level threads per kernel thread. But then if out of these 50, 45 user level threads exit, then you just have 5 user level threads remaining and 5 kernel level threads in action. Once you have one of these 5 user level threads starting to exit also, then you have one extra kernel level thread that is not used, and in that case you start basically removing some of the kernel level threads. And this was designed for mostly multiprocessor machines, and it was used for it was at least tried during some times on Windows, and it was actually the way that it was used with ancient Solaris versions. That's basically before Solaris 9. I'm not sure what Solaris version they have right now, but that is roughly, I think Solaris 9 is something like 2006, 2007 maybe. Even, I can't remember the exact date. Okay, so now you have, and this is the many-to-many user level thread model basically. Okay, and there are plot twists to all of these 3 models. There is one where you have a per processor kernel thread with multiplexed green threads, so a many-to-many threading model, but you have for each processor one single kernel thread. So if you have a multi-core processor with 4 cores, then you'll have 4 kernel level threads, but then you have green threads that get multiplexed on that. Okay, this is one plot twist. The other one is basically what is called scheduler activations. It was actually suggested in 1993. It got some implementation, some momentum back then. The paper that was published that basically described that model got something like 600 citations. This is pretty large number for computing science papers in general. And there basically the plot twist is that you have explicit support for user level threading. So it's no longer that you have green threads, and it's no longer that you have user threads, and it's no longer that you have kernel threads, but you have both kernel threads and user level threads, but the kernel is aware of the user level threads. So that's another plot twist. And for the user level threads, there is a user level thread scheduler that basically talks to the kernel thread scheduler, and that basically schedules the user level threads. That tells basically the user level threads the user level scheduler tells the kernel level scheduler that now this is the user level thread that you should be running. And once the operating system, the kernel level scheduler, decides that it needs to evict one of the user level threads, it will get in touch with the user level scheduler asking for another user level thread. So it's quite complicated, and it's called scheduler activations. And then the who implements the user level thread? That's not the user. Okay, so that's not you and me when you're programming, but someone else. And that someone else, just to add to the plot twist, is either the operating system. So you have explicit support in your operating system for doing that. And that was actually the way that some Windows versions implemented that. Or through a threading library, which is something that is different. There is something that is called a threading library. Well, it basically controls the way that the applications does threading, or Martians basically. I mean, someone from Marsh implements this user level threading scheduler for you. And this is an example of one of the threading libraries that were implemented to basically do user level use scheduler activation. So this is a direct link that you can basically go and check that. And of course, this is almost obsolete. Then so this is basically how screwed the threading model space is. And I think that the most elegant one, the easiest one to understand, is the one-to-one model, which has been almost the Linux supported version. Actually, scheduler activation, some people tried implementing them in the Linux scheduler, but it never got traction, for example. I mean, I think it was suggested it might have even be integrated as optional way to do threading, but it never actually got traction. And we are back to the one-to-one model. We have always been on the one-to-one model actually with Linux. So it's very elegant, very clean. It does not really make life very hard to understand from a programmer's point of view, right? You have one user level thread versus one kernel level thread. Voila, it's over. So enough with this. So let's talk about how we kill the threads. And there is actually a file that's called in kernel, in the kernel folder, that's called /exit.c. And there you have a do exit function that basically gets the thread, that exits the thread that is running, that basically moves the thread from the runnable state to the finished state, basically. Okay, and that's the way you basically kill the threads, using the do exit threads. And we have actually discussed that in some cases, if you kill a thread, the children do not get killed. And in theory, in most operating systems books, they will tell you, yes, they get killed. I have actually given you examples of cases when you can find that they do not get killed. But actually in Linux, there is even a function that's called find new reaper. And that is basically a function that tries to reparent all the children. So if a thread dies, it might call, I'm not saying it has to call, but it might call find new reaper. And that is basically a way for the thread's children to be reallocated to another parent. And that parent can be init. So you can have basically threads that were running in, for example, your database, and then you kill your database, but these threads have been raped to init. And of course, this is either something that you absolutely want, because you want the threads that were starting by a program to keep running, and that program, if that program dies, you want this to continue running. Or something that you absolutely do not want, because once you want your program to die, you want all children to be cleaned out. And this is design choice basically that you need to do in your program. Okay? And do exit basically takes these steps to exit a thread, to kill a thread. And in the beginning it raises a flag that says that it's exiting. And then it calls a function to remove any timers that are associated with this thread. It calls a function to release the memory structure held by the process, and if no other process is using the address space, then the kernel will destroy that part of memory later. Not now, but it just says that I'm exiting, so I'm no longer using this part of memory. And if there are any locks, semaphores that are held by the or semaphores that are held by the process, then they are released. And we are going to talk about locks and semaphores actually very soon, as in the next lecture. And it calls exit files and exit file system to decrement to basically, if it's open, if it has any files that are open, then it closes all of these files. I mean, it tries to exit them. It basically says that I am no longer use these objects. Okay. And as we said that, well, these files can be actually control over hardware, for example, because it's open, the open and close semantic, basically, that we have discussed. Okay. It sets the task's exit code, and that is basically if it was successful, for example, if it was failed. I mean, there are multiple task exit codes, so it sets the exit code that would then notify the parent of how this task was exited, basically, of how this thread exited. And then it notifies the parent that it's exiting, okay? And then it actually calls the scheduler to tell the scheduler that, oh, I have just exited. Okay, so these are the steps that are taken by the do exit system call. The do exit kernel method. So now that we have talked about how we actually stop the task, how the task goes from the running state to the finished state, we now talk about how we do the actual cleanup, which is basically released a function that is called release task. And release task basically takes the task struct that is basically being that task struct that is of the task that is to be cleaned, and starts doing the cleaning process. And the cleaning process is what we have described earlier, that, well, you do not want the task itself to be in charge of removing everything that is related to it. I mean, it does release the memory, but it does not delete the memory. So release task is the cleaner, the cleaning up task, the garbage collector. I mean, it's not a garbage collector in the Java sense, but it's basically the function that goes in and sees what tasks are in a finished state and cleans up the memory. And basically, if the memory is needed by other threads, then it would not clean it up. Okay, and release task basically does these steps to release the memory and clean up. So it calls an exit signal, which calls another which has another call internally, which basically removes the PID to remove the process list. The process PID from the PID hash, which is basically somewhere where you have all the PIDs of the processes that are running. So now that part is removed, you no longer, this PID doesn't exist. You also remove the process from the task list, which is basically the doubly circular linked list we have been talking about. And then the exit signal, after basically unhash process, which kind of detaches the PID, you basically the exit signal releases any remaining resources used by now that task, and finalizes the statistics. Did it finish correctly? Did it finish due to some breaking some rules, and so on, and does the bookkeeping. If that task was the last member of a thread group, so it was basically the last task in a group of threads that were running together, then release task notifies the leader that, well, there's nothing now remaining. You should basically terminate that thread pool, or that not that thread pool, but these threads, basically everything that is related to them. And then it basically frees the pages containing, for example, the kernel stack, the thread infrastructure, and deallocate any cache that has been allocated to the empty task. With this, we actually have covered everything that we wanted to talk about how tasks are handled in Linux. This will not be this is the video I intended to post yesterday, but I basically got it wrong because of my microphone. But now this is hopefully better video, or a better set of videos. I will also record and upload videos today on system calls, or I mean, yes, well, today is not really today because it's probably tomorrow, Sunday. You will get videos on system calls and how they are actually used in Linux, so that you can basically start with assignment 1 if you have not already done so. I know that a few of you have already done so, have thought about it, have read about it, and are probably, they might have even done the implementation already. But the coming video will hopefully make things even easier for everybody, including the people who have actually done it. Maybe they would like to revise what they have been doing. Okay, so thank you everyone, and see you on Tuesday, and talk to you pretty soon, and show you myself on a video.